Good afternoon. I'm happy to introduce Professor Bill Daly. Bill Daly is a VP of Research at NVIDIA and actually also Professor of Research at Stanford. His history is long, the technical history. He was in Bell Labs, was professor at MIT, professor at Stanford, and was CS chair. He did his BSc in Virginia Tech, and his PhD from Caltech with, if you know, Chuck Seitz was his physics advisor. Altogether, he published 250 papers, 160 patents, a lot of awards, fellow of IEEE, ACM, Equick Moakley Award, Maurice Wilkins Award, and more and more and more. I'll let him talk, but before that, if any of you are interested in flying, so take some time to talk with Bill, and he will tell you how to ditch an airplane. Ditch, by the way, is landing on water. How to ditch a single engine on water, what he did near Boston, and came alive. So, Bill.
Thanks, Uri, and pleasure to be here. So I'm going to tell you about some of the work I've been doing lately, and it's really sort of a fun time to be a person doing computer hardware, because now actually a lot more depends on what we do than it has in the past. The way a lot of value has been created over the past couple decades, sort of illustrated by this figure, we get faster computing, better algorithms, and more data, and that leads to more value. Professor Erica Fuchs at CMU is an economist. Actually, you wrote a paper showing that actually most of the increase in productivity of the last couple decades has come actually from increases in computing, and that people apply computing to various human processes, and manufacturing, various service industries become more efficient as a result. But something has happened recently, which is that Moore's law has ended. We are no longer getting process technology giving us the huge gains that we once got. And actually, more importantly, something called Dennard Scaling, where we used to scale the supply voltages with every generation of technology, has ended. Back during the great days of Dennard Scaling, sort of from the early 1980s through about 2005, every time we got a new generation of technology and the line widths decreased by square root of 2, we would get sort of 3x in performance per watt, because we would sort of win 3 times. We would get a v squared win as we scaled voltage, and then a c win as we scaled the capacitance as well. So we'd sort of cube that square root of 2 and get a 2.8. But today we're not getting that anymore. We're getting very little from technology. So we have to continue to figure out how to scale things. Just to show you that Moore's law really is dead. I'm looking at one slide behind here. I need to catch up. This is a figure from our latest Turing Award winners book, John Hennessy and Dave Patterson. Their most recent edition, the 6th edition. What they show is that back in those good years, CPU performance was increasing 52% per year, and today it's increasing at about 3% per year. And so the question is, how are we going to continue to scale performance per watt, this thing that essentially all of our productivity depends on, in the absence of process technology scaling? And the answer is accelerators. And in fact, they say this in their Turing Award talk. I found this very gratifying. Because I've been building accelerators for a long time, and so I thought I would share some of the experiences of roughly 30 years of building accelerators with you. If I sort of distill down these various accelerators, the way they get their performance is really pretty simple. The first is that they exploit parallelism. Arithmetic units are tiny. We can put literally hundreds of thousands of arithmetic units on a single chip. And so you can do parallelism, thousands or 10,000, 100,000, even millionfold. So when I say massive parallelism, I don't mean 16 cores. I mean thousands or more. And that gives you an enormous amount of performance relatively inexpensively. The arithmetic units also take very little power. You can do arithmetic operations for fractions of a picojoule. What takes most of the power on modern chips is moving the data around. The next way we get performance out of accelerators is by specializing data types and operations. Our conventional processors have an instruction set that manipulates integers or floating point numbers. And if you want to do something like compute the cost of a gene substitution, if you're doing genome alignment, that takes many tens of instructions. You can take that many tens of instructions and collapse it to a single logical operation that happens in a single clock cycle in a tiny fraction of that power. That's specializing a data type. It turns out, though, that what's much more important than flattening 100 instructions into one logical operation is optimizing the memory, because the cost of providing the data to that instruction is more expensive than performing the instruction itself. So what all these accelerators have in common is optimized memory, and I'll give you a couple examples of this, where you need to have the memory be very high bandwidth and low energy, which means local. So it's got to be right next to the arithmetic units and providing the data where it's needed. You have to avoid overhead. In a conventional processor, less than 1% of the actual energy goes into doing the payload operations, doing the math. The bulk of the energy is spent fetching and decoding instructions and fetching operands. And so you need to get rid of that overhead, either get rid of it or amortize it over large enough operations that it doesn't dominate. And then very often you have to change the algorithm. So what I'm going to do here is I'm going to go through a couple of these themes and try to show you through example how they work. But before I dive into that, let me observe that specialized hardware is actually pretty much everywhere today, but you don't see it. So any of us who have cell phones, in the cell phone, all the heavy work is done on specialized accelerators. The modems, which often do hundreds of billions of operations per second. For 5G, it will probably get into trillions. The codecs for both still and moving images. The camera image processing if you take selfies with your phone. Modern phones have deep neural network accelerators and graphics accelerators. All of these things, which do tens to hundreds of billions of operations per second, are hardwired. What runs on the ARM cores is the stuff that has a lot of complexity but doesn't actually do very much work. It's the user interfaces, sort of the low compute, high complexity parts of it. Similarly, at NVIDIA, we build GPUs, and toward the end of this talk, I'll talk about how a GPU is an ideal platform to do acceleration. And what we've done with our GPUs is we've used them as that platform, and we've added to them special purpose hardware for a number of different tasks. For computer graphics, we have hardware that does rasterization. It takes a description of a triangle and turns it into a bunch of fragments. We have hardware for texture filtering, so we can basically do a three-way interpolation of a trilinear interpolation of textures at different levels of detail to compute a texel between points of the texture maps. And compositing, so we can basically take a fragment that we've calculated and composite it with other fragments at the same location to compute the value of a pixel. We've also added accelerators for doing compression and decompression. For neural networks, we now do tensor computations very efficiently. I'll talk a little bit about that. And just recently, we announced in our Turing generation GPUs acceleration for ray tracing. This is really two separate accelerators, one that does traversal of a structure called a bounding volume hierarchy. So you can basically find out what set of triangles you need to test a ray against very quickly, and then to actually do the ray triangle intersection test. So let me talk now about how these accelerators get their advantage. And probably the first way they get their advantage is by tailoring the data types. And sometimes the data type is one that you wouldn't find on a conventional machine. It's 2 bits to represent a base pair for genomics, or you're operating in a Galois field, which conventional processors don't have instructions for. But sometimes it is just floating point and integer operations. It's a question of picking the right precision. So for example, for our modern tensor operations, our Turing GPU supports both 8-bit and 4-bit integer precision, whereas in the past people would run these things on 32-bit floating point. And it's a huge advantage because if you look at the multiply that dominates the arithmetic energy, the cost of going from, let's just look at the integer numbers here, from a 32-bit multiply to an 8-bit multiply isn't the 4 to 1, it's quadratic, it's 16 to 1. Because the number of partial products you produce is a square of the number of bits that you're multiplying. So reducing the precision that you're operating on wins hugely. In addition to reducing the actual cost of the multiply, the other reason why it's important to reduce precision is to try to compress the data that you're operating on. And this is critical because, again, memory tends to dominate these accelerators. And if I can make my data sets small, I can keep them in a small local SRAM, where the cost of operating on them is on the order of about 5 picojoules per 32-bit word. If on the other hand I have to fetch them from somewhere else on chip, the cost goes up by an order of magnitude. And by the way, this SRAM and this SRAM are the same. The additional 45 picojoules is wire energy. getting the address to that memory and getting the data back. And if I have to go off chip, it goes up another order of magnitude. So every time I go up a level in the storage hierarchy, it's another order of magnitude energy. So by keeping things small, I can get more of a working set in this small local memory and save orders of magnitude of energy. And as time goes on, this need to be local is increasing because things scale at different rates. If I look at the scaling from 40 nanometers, sort of the chips that we built sort of in our Fermi generation, this is chip we first shipped in 2010, to 10 nanometers, which is sort of order of what we're shipping today, the arithmetic energy reduces about 4x, from sort of 50 picojoules to a little more than 10 to do this is for a double precision floating multiply add, whereas the communication energy drops by less than a third. So the communication energy is scaling at a far slower rate than, this is for 1 millimeter of wire transferring 64 bits. It's basically more than the math to begin with, and it's scaling more slowly. So communication is going to dominate even more in the future than it does today. So now I'm going to start in a set of vignettes about sort of principles of accelerator design. And the first is that the algorithm has to change. And the example I'm going to use here is a bioinformatics algorithm that we worked on with some of our colleagues in biology at Stanford. And the problem is to do alignment both for what's called reference-based assembly and de novo assembly of gene sequences from the newer generation of machines from Oxford Nanopore and PacBio that generate very long reads. They generate reads of about 10,000 or longer base pairs. The longest ones are actually close to 1 million base pairs, but they're very noisy. So when the first ones of these came out from Oxford Nanopore, there was actually about 60% accurate, which meant that 40% of the bases were wrong. So it's hard to match these strings when most of the things you're matching are actually incorrect. So we took the algorithm, which was sort of the state-of-the-art for long-read assembly at the time, called GraphMap, and I had a graduate student look at what could you do to accelerate GraphMap. So it turns out doing these alignments has 2 steps to it. The first step is called filtering, where you use a process called seeding, where you basically take certain seeds within the sequence you're trying to align. You look them up in a database of where a seed is, say, anywhere between sort of a 10 and 15 long set of base pairs, and you then look up in an index where that 10 to 15 is in the sequence you're trying to align to, which is a reference genome if you're doing reference-based assembly, and it's actually the concatenation of all of your reads if you're doing de novo assembly. And by doing this seeding, you then reduce the amount of work you have to do with dynamic programming. So GraphMap spent almost all of its time doing very thorough seeding, because on conventional processors, dynamic programming is expensive. So there's a very expensive filtration step that only gets 3 hits out, and you do very little dynamic programming. And it turns out this seeding is entirely memory limited, right? You're doing references to an index, which is tens of gigabytes in size, right? This index has to have an entry. It's basically a 4 to 8 byte entry for every one of the 3 billion base pairs. And so it's many tens of gigabytes. And you're completely going to be limited by the bandwidth of the DRAM that you need to hold that. So when the student did his best work at what he could do to accelerate GraphMap, the answer was we could get maybe 3x. And at that point in time, we were about ready to cancel the project and move on to more productive things. But I asked the question, what could you do if you were less thorough about filtering to move more of the workload to alignment? Could you do things to reduce the workload here, which is hard to accelerate, and push more of the workload to alignment, which is easy to accelerate? So the first thing we did is we basically came up with newer algorithms, a much lower overhead filtering algorithm we call DSoft. So it gets a lot of false positives. So whereas we get 3 hits here, basically one of which is correct. Here we get 1,700 hits, one of which is correct. But that's okay. If we ran this in software, this would basically slow us down by a factor of 2. But what we've done is we've now changed the problem from being one that's limited by DRAM bandwidth to being one that's limited by dynamic programming. And we know how to build hardware for dynamic programming. So the next step in accelerating this is we built a little systolic array to do dynamic programming with a bunch of processing elements that basically walk diagonally across the matrix you fill in for dynamic programming. And we can speed it up. We basically speed up the dynamic programming part by many thousands, but overall it gives us a 380 times speed up from where we started. So by refactoring the algorithm, we can do more work where it's easy to accelerate, less where we're limited by something fundamental like memory bandwidth. And then most of the rest of what we did was really about optimizing the memory. The first was to get some memory level parallelism. The conventional algorithm basically is doing the seeding from a single core, and as a result, it winds up not being able to keep more than one memory channel busy. By basically walking many seeds simultaneously, we're able to get a 4x speed up because we have 4 memory channels to operate on. And then what we observed is that in addition to basically walking the seeds, every time you get a seed, you have to decide whether that aligns or not. I'll go through the actual algorithm that does this later. And if you do that in main memory, the data structure here is sort of 64 megabytes. It's bigger even than the last level cache. It winds up interfering with the relatively sequential accesses to the seeds and basically slowing down the entire memory system by getting these bin updates interleaving in with the walks of the seed tables. So by building a specialized memory structure to hold these bin counts, we get sort of a 15 times speed up. Finally, we can observe that we have these 2 separate steps, the filtering step and the alignment step, and we can pipeline them. So we're basically filtering for one batch of reads while we're aligning the previous batch of reads and run them at the same time. That gives us another 1.4. So from where we started to where we ended, we get a 15,000 times speed up. That's a lot more interesting than the sort of 3x that we could have got had we accelerated the original algorithm. So the message here is that you can't just take somebody's piece of dusty code and accelerate it. You have to understand the problem being solved and sometimes shift the work around to the parts that are easy to accelerate. The next message is really that memory dominates, and actually in several ways. And in fact, when we started this problem, this project, one of the first things we had to deal with was figuring out how to do the dynamic programming in an efficient way. Because typically what we have is something on the order of 15 million reads of 10,000 bases each. And we're going to have sort of 2,000 hits each, so 2,000 alignments we have to do for each of those. So it's 300 tera alignments that we have to do. And if you think about doing the whole alignment, you would have a 10,000 base pair read here, and then you would align it against sort of 10,000 bases from your reference sequence or the concatenated sequence of all the reads if you're doing de novo, starting at the point where the seed hit tells you to start. And this matrix then would be 100 million to fill in, and that's too large to fit into on-chip memory. So we looked at a bunch of alternatives to filling in the whole matrix. One that many people do is called banded Smith-Waterman, where you simply have a band of this matrix you fill in. The problem is that most of the read technologies have different insert rates and delete rates, which means this path of the optimum place doesn't stay on the diagonal. It wanders a significant amount off. So over the 10,000, you could easily be off by 1,000 at the end. And so either your band has to be almost large enough that you couldn't bother, or you're going to wander out of the band with the optimal read thing. Ultimately, what we discovered is that we can generate optimal alignments if we overlapped. So if we do an alignment which is, say, 500 by 500, and then we overlapped it by 200, within that 500, the optimal path was extremely unlikely to drift out. So it turns out I'm not going to go into the details of this, but when we later tried to apply the same technology to whole genome alignment of multiple species, this wound up not working because if you're aligning human to something very distant than human, you will get huge jumps, and you could jump out of that overlap region. And we actually had to come up with a different alignment algorithm that was more tolerant to large jumps. But if you're doing an assembly of human to human, this works really well. And in fact, it's always generated optimal alignments for the right set of overlap values. And so by doing this, what you do is you track the actual path, even if it wanders far off the diagonal. By taking over these 10,000, you'll have 20 of these blocks of 500 overlapped with each one. And you'll do the dynamic programming, and at any point in time, your memory footprint is 500 times 500. It's not 10,000 times 10,000. So you wind up with a memory footprint that fits very easily in on-chip memory. So in the special purpose accelerator for this, these processing elements are tiny, right? They're little specialized pieces of logic that compute this cost function. They actually look up in a table the cost function of substituting one base pair for another or inserting or deleting, depending on whether you're opening. It's an affine gap penalty, whether you're opening a gap or continuing a gap. And so we can put 4,000 of them down on a chip, and that's actually a tiny fraction of the chip area. I'll show you most of the chip area is memory. And those 4,000 is 64 arrays. So we're basically doing 64 alignments in parallel. We've got plenty of reads to align, so there's lots of parallelism on the outer loop here. And the inner loop is 64 elements in each array that's basically walking a diagonal. Now, our arrays, the tiles are bigger than 64. So we basically advance, you're walking the diagonal for the dynamic programming this way, and we'll basically walk 64, then the next 64, and then the next 64 until we fill the whole tile, and then move on to the next row. And so this is able to do the dynamic programming fast enough that it winds up not mattering. It's 80,000 times speed up compared to a CPU. We're doing 40,000 operations per cycle. Now, the way to see that memory dominates is to look at both where the area and the power in this accelerator go. The area is entirely in the memory. If you think about it both as the dynamic programming part of the chip and the filtering part of the chip, they're both memory dominated. In the dynamic programming part, we have memory that's basically keeping all of the scores computed for this tile of the dynamic programming matrix, because when we do the backtracking, we basically need that data to basically walk back and construct the optimal path. During the filtering part, we basically keep this, there's 64 megabytes of bin count RAMs that are basically keeping track of the seed hits to see where the next candidate is to go do the dynamic programming on. And that completely dominates, that's more, combine those two together, it's more than 3/4 of the die area. And this is, well over 90% of the area of the filtering part. And then when you look at where the power goes, it's also completely dominated. This 15 watts, more than 11 watts of it is in the power of the SRAM. So the first approximation, you can estimate both the size and the power of an accelerator chip by basically looking at where the memory is. Now, whenever I propose specialized memories to people, people point out to me that building a specialized memory is 10 to 100 times more expensive per bit than commodity RAM. First of all, it's less dense. You're typically doing SRAM rather than DRAM. DRAM has a density of 1 bit every 2 features squared, right? You have two lines by 1 line on a chip is a bit cell, whereas SRAM is 5 by 2. So you're off by about an order of magnitude in area, SRAM to DRAM. And then you get another nearly order of magnitude by sort of the learning curve. People build DRAMs in very large quantities. They're produced in very low margins. And so they're inexpensive. It's $5 per gigabyte to buy DRAM. SRAM is much more expensive. But let me show you how we use specialized SRAM in this genome accelerator, and how, even though it's 100 times more expensive per bit, it's actually cheaper. So the way the seeding algorithm works is we take the two sequences we're trying to align. So this is our read, and this is, say, the reference sequence. We're doing reference-based alignment. And we take seeds, which are basically consecutive base pairs here, or they can actually be non-consecutive patterns of bases at certain positions. And we find out where those seeds appear in the reference sequence. We've already built that index by walking the reference sequence. And I'm going to do it here, taking 2 at a time. 2 is too small to be useful. You'll typically do maybe 12 at a time, anywhere between, say, 10 and 15. And remember, these are die bits, right? So 10 at a time, you basically have a 20-bit index. So I will basically take the 2 base pair sequence here, GT, so it's 4 bits in this case. I'll look up in a table where the seed table starts for GT. I'll then look up from there to find out what positions need to be updated. And I'll say, okay, I need to update 31 and 12. And so I'll go to position 12 and position 31, and I'll increment the bin count at that point. Then we'll walk to my next seed, which in this case is GC. I'll take the GC here, which starts at position 21 and goes to 17, and I'll walk those positions and add them to the index. I'll take the next one. In this case, I've stepped by 1 instead of by 2. CT is the next one. I go to these locations, and where it overlaps, I will only increment by the 1 that it's incrementing, because I'm basically extending a match that was already there, where there's no overlap. Increment by 2, so I'm basically counting the number of bases that actually matched. And I continue doing this. I get TT there and TG here, until after I've walked however many seeds are typically done, and again, I'm going to be using seeds maybe of length 12, and I might do 20 of them. And when I finish, I have relatively high confidence that I pass a threshold that, that if there is something which will match in the dynamic programming, it's going to be one of these that it's exceeded my threshold. In this case, my threshold is 5. These two are over 5 on the matching bases. I will pass them on to dynamic programming. Now, the way we do this in hardware is with just a very simple engine. We have a set of state machines that walk the seed tables in DRAM, right? So they'll take the seed, they'll look up the starting position of the seed table, and then they'll basically just start reading the positions from that point. They feed those positions through an on-chip interconnection network into 16 bin update SRAMs. And these bin update SRAMs just add the number of matching bases to a running count in the bin updates. And then these things do two things. One is they basically, when you first increment a bin above 0, they record that fact, and this just lets you reinitialize for the next go. You need to basically zero everybody out. You don't want to walk every bin and zero them. You just want to do the ones you actually hit. And then if you've exceeded the threshold, it sends it to the output, because that's going to feed downstream into the candidates for dynamic programming. And so here we're able to, every cycle, feed one of these bins through, access these memories, and by having this on-chip memory, we get nearly a 16-fold speed up compared to doing this with DRAM. And we also make the bandwidth of these seed walkers much faster, because they're doing sequential accesses. And if we had to basically do row precharges to go and do the random accesses for the bins, we'd slow that down considerably, even with a good scheduler. So if I do a calculation of the cost, I have to take into effect that cost has a time dimension. And the way to think about this is, suppose I'm running a center where I'm doing genome assembly. People are feeding me reads from, say, a PacBio machine, and I'm sending them back assembled genomes. And maybe they're feeding me these, every 10 minutes I get another thing to assemble. If it takes me 10 minutes to assemble it, I need 1 machine. But if it takes me 100 minutes to assemble it, I need 10 machines, right? So the cost is multiplied by the amount of time it takes to do something. So the cost equation is how much time it takes my engine to do something times the number of bits in one memory, times the cost per bit in one memory times the number of bits in that memory, plus the cost per bit in the next memory times the number of bits in that memory, plus a bunch of other terms, plus the cost of the processor. But all of this gets multiplied by time. If I slow down, right, I need to buy more machines to achieve a given level of throughput. So if I take the Darwin filtering algorithm and call that 1 in terms of time, running all out of DRAM, if I didn't have the acceleration of those bin count memories, is 15.6 times slower, right? Darwin has to pay, I'm going to say, a cost per bit of 100. I'm going to give it at the far end of the spectrum. It'll be 100 times as much per bit for the on-chip SRAM, and I've got 64 megabits of it. And I'll say the cost per bit is 1 for DRAM. That's my reference. I have 128 gigabytes of it for the seed tables. And if I do it all in DRAM, I just have 128 gigabytes of DRAM. This costs more than an order of magnitude more because of that acceleration factor. Even though this expense here is pretty high, right? It more than pays for itself by the 16x improvement in performance. And that's really the motivation to build specialized memories. So now that we've sort of established that memory is critical, it should follow that compressing things is critical. And what we found, especially for doing deep neural networks, is that they're fundamentally sparse data structures, and both the weights and activations can be compressed using various techniques. And so my former graduate student, Song Han, who's now a professor at MIT, and I published a paper in NIPS in 2015 showing that we could prune neural networks. We could prune fully connected layers and recurrent layers, typically throwing away 90% of their weights, so that the resulting density was 10%, And for convolution layers, we could prune them down to densities of 30 to 40% with no loss of accuracy. We went on and we published, so this is basically sort of the kind of sparse matrix that results after you do that pruning. And it's basically statically sparse in the weights, and it's dynamically sparse in the activations because the ReLU nonlinear function takes all the negative values and turns them to 0. Typically, only about 40% of your activations are non-zero. And for convolutional layers, 40% of the weights are non-zero. For fully connected layers, only about 10% of the weights are non-zero. You typically will encode that matrix in what's called a compressed sparse row or compressed sparse column format, where you basically have an index that tells you where each column starts. Like one column will start at 0, and that gives you W00. The next column will start at 1, the next at 2, and so on. And then you basically have to walk this relative index to figure out where each of these weights is supposed to actually go. We also went on and we published some work where we basically showed how we could take the number of bits per weight and compress it by doing non-uniform quantization. In fact, we could do scalar quantization with a code book that was trained through stochastic gradient descent. We actually just feed the gradients back into the code book. We move each of the code words around as we train. And the pruning, this is basically shows the distribution of weights we get after pruning. The pruning takes the stuff around 0 out. So your distribution of weights is sort of this bimodal distribution. You'd like to have your code book values not uniformly sampled. This shows what you would get if you had 4-bit weights. If you uniformly sample, you're spending a lot of code words out here where there's essentially nothing happening. If you instead train a code book, you concentrate your code words where interesting things are happening, and you get a lot more out of each code word. You can get by with fewer bits and the same level of accuracy. Now, when we submitted the original paper on both of these ideas, we were originally criticized, particularly on the one about pruning, with what was really a very legitimate concern. One of the reviewers pointed out that most sparse matrix packages only break even at about 1% density. Some of them actually it's like 0.1% density. So your matrix has to be really sparse before it pays to use the sparse matrix package. And we were operating in this nether region of sort of 10 to 40%, where conventional wisdom is you're better off just running it like a dense matrix, and you get essentially no advantage. But what we showed is we could build a piece of specialized hardware, we called our efficient inference engine, and it was an array of processing elements. Each processing element operated on a certain fraction of the matrix. And each processing element would get an activation to multiply against its fraction of the matrix. That activation would be on a certain column, so you'd have to look up that column, and we had a pair of pointers. You'd look up that column and the next column. They'll basically give you the starting address and the ending address to walk the elements of that column. And then the sparse matrix SRAM would give us for every entry 2 things. It would give us the code word, basically the thing we had to look up to get the actual value of that entry, and it would give us the number of zeros between the last entry and this entry. So we'd keep a running sum of the row that this would occur in. We would use that row to fetch the accumulator we needed to add this into. In parallel with computing that running sum, we would decode the weight, do the multiply accumulate operation, and store that back. And by doing this, we were able to get energy-wise break even on sparse matrices at around 60 to 70% density, because we were typically doing 8-bit code words, and we were storing the indices here with 4-bit increments, 4-bit run length encoding. And because we were basically specializing some hardware to walk this sparse matrix structure, it wasn't a long sequential computation of reading something from memory, very often missing all the caches, reading it back. But every cycle, we could basically generate another pair of code word and increment to the next row, and basically do a multiply add per cycle out of this without central overhead. This is also a nice illustration of how memory really does dominate. This is the layout of one of the EIE processing elements. And what you see is the arithmetic is this little thing in the middle here. And everything else is memory. The pointer even and pointer odd tables for the compressed sparse column format are here. those are these here. And then these are actually where the sparse matrix is stored. So it's basically a very specialized memory. But the data doesn't have to travel very far, so it's extremely energy efficient. Another thing I found in building a lot of these accelerators is that simple parallelism often beats better algorithms. And the example I used to illustrate this is we built a SAT solver. The state of the art, SAT solving advanced a lot when in 1996 people started learning clauses based on conflicts. And then in 1999 or 2000, the people at Princeton came up with this SAT solver called Chaff that used a clever data structure to basically, for every clause that was not yet driven unit, keep 2 literals for that clause, with the theory that when you were searching on a literal, if it didn't match one of those 2, that clause wasn't about to go unit, even if it matched some other literal in the clause. And then there was a long index structure where for every literal, you'd keep a list of just the clauses that had that literal. What we observed is that we could actually go faster if instead of doing the watch to that Chaff did in the complex index structures, if we just broadcast every literal as it was determined to every clause. So we basically were building a specialized memory, as an associative memory. We would determine a literal. This could be determined either because we had bottomed out our propagation and we get to choose another literal to determine, or it could be based on the propagation of a previous literal driving a clause to unit, and then that clause propagates a literal. And then we just start propagating it. We have an on-chip mesh network, so it propagates to its neighbors, compares to all the clauses in those clause units, continues propagating, and at some point in time, it gets a match, right? And this, actually, it may be setting literals here, but here it gets a match that drives a clause unit, so it's determined another variable. So while this literal is still propagating, that one can start propagating, and they can propagate in parallel. And by doing this, we're able to operate for the propagation part of the computation many hundreds of times faster than if we did this on a CPU using the 2-watch and the index approach. In fact, the 2-watch and the index approach essentially serializes what we've made a very parallel operation here. And this brute force parallelism just really wins. We're able to keep the operations very local. And even though we're doing a lot of comparisons that if you use the index structure you could avoid, it doesn't matter, they're cheap. It's cheaper to just do the comparisons than to walk an index and only do the comparisons that you know are going to hit. Another thing we found with the SAT solver, and it's kind of a corollary to Amdahl's law, is you have to accelerate the whole problem. So when we started the SAT solver work, we were really excited because our propagation part was 300 to 500 times faster than running on the CPU. This shows for a bunch, we basically use it as a benchmark suite. There's a SAT competition every year, and we basically took a bunch of the benchmarks from the last year's SAT competition and fed them into our propagation unit. And this is a logarithmic scale here, and this is how long it takes on the CPU, and this is how long it takes us to do it. So we were nearly 3 orders of magnitude faster, so we thought, oh, this is great. And then we benchmarked the typical SAT solver. So this is basically benchmarking mini-SAT, and most of the SAT solvers people use today, I think the one that won the competition last year is called Glucose, are based on mini-SAT. Glucose is based on mini-SAT, several of them are. And what we found is that this propagate phase that we were accelerating, is the green part of the bar here, only accounts for on average less than 80% of the execution time. Which, again, using Amdahl's law arguments, if we drove that to 0, we could get a 5x speed up, and nobody would be very excited. So what we realized is that in addition to accelerating the propagate, we also had to accelerate learning the conflict clause, which is a lot of what the analyze part is here, and minimizing the conflict clause, where basically we look at other clauses that we have, and we use it to knock literals out of the learned clause. It turns out that there are parts of the SAT computation, for example, choosing which variable to determine next if you've run out of propagation, and choosing which learn clauses to delete, that happen infrequently enough that we don't have to accelerate them. We continue running them in software, because then we get all the flexibility of being able to exactly match the logic of whoever currently has the best algorithm for those. And it's complicated heuristics that people tune. But the big part of these graphs, we basically have to accelerate the whole thing or we won't get there. And we ultimately, by accelerating the learning of clauses and the simplifying of clauses, we're able to get about 100x. And part of the lesson we learned there was to specialize just what you need and not too much, right? So we're specializing the things that matter, that drive the performance, but we're not specializing the things which give people flexibility, you know, determining which variable and determining which clause to delete. I also learned this lesson actually many years earlier when I was at Caltech and at Bell Labs. I built a series of simulation accelerators, and the first one was a simulation accelerator from MOSIM, which was a switch level simulator. It basically would simulate MOS circuits and basically resolve conflicts between transistors pulling up or pulling down. If you had fights, it would actually drive an X onto the output. You could have data storage on the nodes. And it was sort of at the time the way most people would simulate complicated MOS circuits. Eventually, the way the industry turned out is nobody uses circuits like that anymore because they deem them too dangerous. It's too risky to have your chip not work because you did some very clever dynamic circuit. But at the time, they were pretty widely used, and switch-level simulations were pretty popular. And what I had done is I basically hardwired every stage of the pipeline for MOSIM. The simulator was blindingly fast, 1,000 times faster than a CPU, but all it would run was MOSIM. And so, wonderful, Microsoft is checking for updates. How do I get rid of that? Cancel. Okay. And so when some people at Bell Labs approached me about building a simulator to accelerate what at the time was their logic simulator, a simulator called Modus. When I talked to them, I discovered that there was not one Modus. There was the unit delay Modus, which is what people use most often, where every gate had a delay of 1. There was multiple delay Modus, where they would basically do an extraction of the chip and assign a delay to each gate based on its drive and its load. And there was a fault simulator that also kept track. You could inject faults and see if you had coverage of faults over a test suite. And so what I decided, and having sort of looked at the logic I designed, completely hardwiring the previous one, is, let me jump 2 slides ahead here, is that this is the multiple delay Modus pipeline. And it has a couple parts. One part where you basically evaluate the gates, right? You basically have an input table, which is the current input to the gates. You look up the gate type. You basically look up a truth table. Then you look up a delay table depending on that gate. You detect whether the gate has actually changed value or not. And basically, if it has changed value, you have to then go and schedule when, put into a time wheel when the signal is going to change. There's a check for oscillation. You fan out to all the output gates of that, and then it feeds back around and evaluates the next gate. So I looked at what went on inside each of these blocks for a switch-level simulator that I was still interested in building, for the unit delay, the multiple delay, and the fault simulator, and I decided that they all depended on a couple very basic operations. Let me go back to this slide. And so it could really be boiled down to doing table lookups and doing simple field operations, and that you typically, this was a 16-bit mini computer of sorts, and the field operation would extract, a 1, 2, 4, or 8-bit field out of the 16-bit field. In fact, I think I could even have things that were not powers of 2, and then do something to it. And by doing that, I could make most of those operations take, if not 1 clock cycle, 2 or 3 clock cycles. And so rather than building a whole bunch of different hardwired units, I built one processing element. This was a chip that we did in 1.25 micron CMOS technology. This is around 1984, 1985. That was sort of state of the art at the time. And they could talk to each other very easily. This Q unit, as far as the microprogram RAM had, there was 32 registers here. And one of the registers was mapped to reading the head of the queue. And so you could configure this into the simulation pipeline via a switch so that one of these PEs would talk to another PE. And when you wanted a new data value, you'd simply read a register. And there was a FIFO in here. And if the guy at the other end hadn't produced a value yet, you stalled. And if you were the rate limiting step, he would fill the FIFO and he would stall. But it meant when things were humming along, reading the next value took essentially no time. You'd be doing an operation in the field operation unit. You'd specify the Q as one of the operands. And in one cycle, you would do that operation. Very often, you would produce the result and stick it in the output queue. And you could, very few of the pipelines ran at 1 per cycle, but very few of them ran at slower than 1 every 3 or 4 cycles. And so it was about as fast as you could have done if you'd hardwired it, but it was completely flexible. And one thing I discovered only years later was that this machine lived long after I left Bell Labs for like another 15 years. It was revved through like 4 generations of technology. And the way I found this out, it's just kind of an interesting anecdote, is I had a student in my logic design class at Stanford who says, "My dad knows you." And I go, "Yeah? And, what is his name?" And I didn't recognize the name. And he said, "Yeah," he said, "he inherited your machine at Bell Labs." And so I called the guy up, and I found that I had done this in 1 1/4 micron CMOS. And of course, they dumbed it down. I had all sorts of interesting dynamic circuits in here to make it fit into a very small chip. That microprogram RAM was 1 TD RAM that the process people were horribly afraid of. As they redid it, they made it SRAM. They got rid of all the dynamic circuits, but they revved it. I did it in 1 1/4. They did it in 0.7 and 0.5 and 0.35 and 0.25 before they finally retired it, because they built, ultimately thousands of copies of this, and it was how all of the logic simulation for many years was done in the Bell system. This is the high-level block diagram. Rather than hardwiring the pipeline, there were, each board had, I wish I had a photo of the boards here. Each board had 14 of these processing elements with external RAM, and there was a 16 by 16 crossbar switch that basically took 2 cycles. So you would produce a result, 2 cycles later it was in the FIFO on whoever was your consumer, and it was all just synchronized with ready valid handshakes. So whoever was the rate limiting step set the thing for the whole pipeline, and then you could tie a bunch of these together. This is a 16-port switch. There were 14 PEs, one for a little microprocessor that initialized everything, and then you would tie that into other switches via a global switch. So you could build much larger systems. But the message here is you can actually make things very efficient without giving up flexibility if you accelerate only what needs to be accelerated and not everything. As a hardware designer, you get very tempted to actually just hardwire everything. It's an easy way to do it. And it requires a little more thought to think about what needs to be accelerated, what can you leave programmable. So that leads me into sort of this part of the talk on platforms for acceleration. GPUs in some sense are ideal accelerator platforms, because remember the speed up in accelerator comes from parallelism, specialized operations, and basically very efficient, very local memory. And that memory usually involves some communication as well. The GPUs have a really nice high bandwidth hierarchical memory system, and you can configure that to different applications. Memories don't care what the bits they're storing mean. Those bits can be base pairs for a genomics application. They can be vertices for a graphics application. They can be activations or weights for a deep learning application. If you have a really great memory system, it will be really great for all of those. The GPUs give you sort of a substrate of programmable control and operand delivery for the parts of the application that don't need to be accelerated, so you get a very flexible platform. And then they got great places to bolt on domain-specific hardware. So as an example of this, this is our Volta GPU. It's sort of 1 generation back at this point. We just announced Turing. Volta was a generation before that. But for deep learning training, Volta is still pretty much the best available. Turing sort of matches it, but does not exceed it for training. Turing is a lot better on inference. And the reason it does so well on deep learning is sort of a combination of having really high memory bandwidth, this 32 gigabyte HBM at 900 gigabytes per second, and having these things we call tensor cores. And so when at NVIDIA we first got very excited about deep learning around 2011, and we started some projects in NVIDIA research looking at accelerating that. We considered building things very much like the Google TPU that would just do deep learning, basically just be matrix multiply units. And we concluded that would be a bad idea. And the reason we concluded that is we basically found that if we built a specialized unit and attached it to a programmable processor, we essentially got everything we would gain by building the completely specialized chip, but we also got flexibility, the ability to write programmable layers, and use the chip for other things as well. So instead we came up with our tensor cores, which are basically specialized matrix multiply units. What the tensor core does is actually we never called it a tensor core. That's what the marketing people called it after we were done. What we called it was HMMA, half precision matrix multiply accumulate. It's an instruction that takes 2 4x4 matrices in half precision, FP16, multiplies them together, basically, does dot product of each row with each column, takes the results of those dot products, and adds them into a FP16 or more often FP32 result matrix. So this one operation, you can sort of think about it as that little figure up there. Each of the gray cubes is a multiply, and then the sums go vertically. This does 128 floating point operations. And by doing that, it amortizes the overhead almost entirely. These are scaled numbers. I'm not allowed to use the real numbers, but the proportions are exactly the same. So these are scaled numbers from a 45 nanometer process. Back in our Kepler generation, the biggest instruction we had was a half precision floating multiply add. That did 2 ops, 1 multiply, 1 add. That takes about 1.5 picojoules energy. And the overhead, since actually fetching and decoding and fetching all the operands is about 30 picojoules, is 2,000%, right? So if that's what you're running against, a specialized accelerator could basically do 20 times as well. In the Pascal generation, we introduced the dot product instruction. We had a half precision dot product 4 instruction. So that does 8 operations, 4 multiplies, 4 adds. It's a dot product and accumulated. So it does the dot product and adds to another scalar. So that does 6 picojoules, 4 times as much as that. Now you could do 5 times as well if you build a dedicated accelerator. But with the HMMA doing 128 operations, it does 120 picojoules of payload math. So the best you could do if all you did was build a matrix multiply unit is 27% better. And we deemed that it wasn't worth 27% to have to do a completely different chip and to lose the flexibility of having the programmable unit there. And in fact, it's in many ways better to have a bunch of these 4x4 matrix multiply units than to have the really enormous matrix multiply units. I mean, the original Google TPU is a 256 by 256, and if your matrices aren't that big, you don't get to use it completely. So in fact, the vision we have for future accelerators, and this raises a lot of research questions, is that people will write programs, and they'll start out by mapping them to whatever they have available at the time. But as they find out where the real bottlenecks are, where the opportunities for specialized operations, for specialized memory accesses are, you'd like to have this mapper in runtime, not just map pieces of your parallel program to the generic streaming multiprocessors, the general purpose processors in the existing accelerators. You'd like to be able to run synthesis programs and generate new accelerator cores that you could drop into this substrate and build this. And it actually raises a lot of interesting questions. What are the right tools for programming this? You'd like to program this in a way that really expresses all parallelism. Most people kind of decide what parallelism to expose and then kind of hide the rest. They turn it into sequential operations. You'd like to expose the maximum amount of parallelism so you can decide what could be accelerated. You'd also like to be able to very easily take parts of programs and pass them out to a high-level synthesis system. People have pretty good high-level synthesis today that if you express an operation unit in C++, existing HLS tools will do a pretty good job of synthesizing that into a piece of hardware. You can usually do better with a good graduate student, but they're getting closer to graduate student quality all the time. And then another big question is, how do you make it economical to actually build the final product? Even if you, so it takes us $3 billion to develop a next generation GPU, but most of that is actually designing the substrate. It's designing the really efficient memory system, the communication, the streaming multiprocessors. Designing an accelerator is more of a sort of $1 million in terms of the labor for doing the design operation. But to tool a new mask set is, in a modern process, is tens of millions of dollars. How do we get around that? And so you have to think about techniques like, could we basically do these, a generation of technology back and basically stack them with through silicon vias on top of existing either packaging technologies that will let us build small accelerator blocks and put them into the larger systems. So let me wrap up because I think I'm actually over time. We really need to continue scaling performance per watt even though we're not getting anything from process technology anymore. And the way to do that is with accelerators. There are a couple lessons I've learned over many years of building accelerators. First, the algorithm typically has to change. If you try to accelerate an existing algorithm, you often find it's limited by something that can't be accelerated, like memory bandwidth. But if you turn the algorithm around a little bit, you can get the same result. Our gene sequencing exceeds the sensitivity of the algorithm we're replacing, but it does it in a way that we can accelerate, whereas the old way you couldn't accelerate. It's really all about the memory. And in fact, you have to manipulate your memory so you can keep the interesting parts of the computation on chip in small memories that are right next to the operation units that are operating on them. That's how you get good performance. Very often you actually have to come up with new algorithms to keep the memory footprint small. And things like sparsity and compression are your friend because they let you take a certain data structure and squeeze it into a smaller memory where you can basically get more efficient access. Simple parallelism wins. You know, the watch 2 and the complicated index algorithms in the SAT solver are fewer operations and asymptotically fewer operations. It's a n versus log n kind of thing. But you have lots of parallelism, and doing a broadcast to an associative memory is a cheap thing to do. It's better just to compare against every clause than to spend a lot of work figuring out exactly which clauses to compare against. And then, you know, there's this whole issue of not specializing more than you have to, both in the example of the simulation accelerator, where by building a relatively simple microcoded unit, I could get the same performance that if I hardwired it, but I could support a lot of different simulation structures, and it actually allowed it to survive over time. That simulator changed a lot in the 15 years that that machine got revved through multiple technology generations, but the underlying architecture was programmable enough that it survived those changes. And GPUs are really an ideal platform for providing the sort of general purpose unit that you can then add special purpose blocks to. They've got a really efficient memory and communication system, and then you can bolt on custom blocks. With those custom blocks are tensor cores for deep learning, ray tracing cores for ray tracing, or other cores that we've not yet come up with for different applications. And in the future, I think we need good tools to help us both map programs to such structures and to take programs and tease out, and maybe with some direction from the user, parts to be turned into custom blocks and other parts to be mapped to the general purpose hardware. So, thank you.
Any questions?
Yeah.
Yeah, two approaches that you didn't mention, I think. One is in-memory processing, and the other is, that's called FPGAs, reconfigurable and data flowing through the computation.
Yeah, that's a really great question. So I'll repeat the question so it's on the mic and gets recorded. So the question is, two approaches I didn't talk about. One is in-memory computing, and the other was FPGAs or reconfigurable processors. So I actually did talk about in-memory computing, but I didn't call it that. It was really, you know, if I go back to things like when I was doing this DSoft algorithm, this is in-memory computing, right? What matters here is that I have these bin count SRAMs, and I'm doing the update logic right next to the bin count SRAM. What I'm not doing is trying to do this at the DRAM. And you could argue, well, why don't I put these things next to the DRAM? And it's because on chip, I can basically put down a whole bunch of these SRAMs. And by the way, the same thing is the case on the PE arrays, where I'm basically keeping the backtracking pointers for the dynamic programming. That's in-memory computing. These things are almost entirely memory chips, right? If I go back to here, let me, right? All the area here is memory. So this is in-memory computing. I've just added these little units that do the bin count updates to the filtering part, right? These are the logic, those are the bin count updates. 6.2 square millimeters of logic for 300 square millimeters of RAM, right? That's in-memory computing. And for the dynamic programming, I have 17.6 square millimeters of logic in those 4K processing elements that are walking the dynamic programming matrices compared to 68 square millimeters in the backtrack RAMs that are storing the backtrack pointers. So this is in-memory computing, because the key to accelerators is basically keeping things in small local memories you can put the logic right next to. A lot of people have tried to propose doing this by adding logic to DRAM chips. And in general, that has a couple problems. One is that DRAM processes are optimized for building memory cells. Memory cells these days involve really tall cylindrical capacitors, and they make really cruddy logic devices, in part because your contacts have to be as tall as those capacitors, and you wind up with very resistive contacts. The devices are slow. It's a bad process to build logic in, and it's expensive to build logic in because the DRAM is easy to make redundant. DRAMs have over 99% yield because they typically have enough redundant bit cells that they can swap out for the ones that are dead. If you start putting any logic down there, the yield drops dramatically because those typically are not redundant. You could investigate doing that, but typically it's better to go ahead and pay that 10x to 100x premium for the cost per bit of these specialized memories and put the logic right next to it in the logic process. I think that it may be the case that with sort of 3D stacking, people will get to the point where they can put a logic process on top of the DRAM process, separately test them, and move, and that may make some sense, but we're not there yet. And then your other question was FPGAs, and FPGAs are basically bad ASICs. And so let me explain that. So the parts of the FPGA that are hardwired, so many FPGAs have DSP units, some have floating point units. Those are great. They're every bit as good as hardwired ones because they are hardwired. But if you're building logic out of LUTs, the experiments we've done show that the factor is about 100 in both area and power. So it's 100 times the area, 100 times the power to build logic from LUTs than it is to basically build logic with standard cells. Now we actually have done this. Darwin is available right now on both the Microsoft Azure cloud and the Amazon cloud. They both have FPGA instances, and the students involved in the project have ported it to both. And what it does is, instead of getting 15,000x, which is what you get with the ASIC, you get like 150x, which is still pretty good, but it's not 15,000. A question back there.
Why did the accelerators are using the half-precision type and not B-flow as the rest? Many new accelerators
Yeah,
are using
yeah.
B-flow.
So the question is, why are we using half precision rather than B-float, which we actually refer to as E8M7. It's an 8-bit, it's basically a truncated FP32. It's an 8-bit exponent and a 7-bit mantissa. Trying to think of what I can say about this. We think that both of those representations are good in different ways. And when we were doing Volta, which is a part that was we first shipped a little over a year ago. We announced it in May 2017. A lot of the applications we were looking at needed the additional bits of mantissa more than the additional bits of exponent. We actually have built arithmetic units that work both ways. And then when we ship a certain product, we decide which one best meets the needs of the customers for that product. Yeah, Jacob.
Who are the customers for special hardware like this?
That's a really good question. So who are the customers for special hardware? So for deep learning, that's easy. It's everybody, right? Every application is using deep learning these days. For the other applications, the customer base is narrower. So for example, for the genomics accelerators, it's people who do long-read sequencing. Our latest genomics accelerator that I didn't talk about is actually aimed at whole genome alignment between multiple species. And they were actually aimed at biology researchers, right? They're people who are trying to recreate phylogenetic trees by comparing different species' DNA, finding out what genes are actually different. It's trying to answer some fundamental questions of biology about what makes one species different than another by looking at which genes differ. And actually, sometimes it's not the genes. Sometimes it's the regulation regions that differ that actually cause the differences. But the problem is that as you get narrower and there's fewer people to sort of amortize the development costs over, it's harder to justify building a special purpose accelerator. And so it doesn't mean that even if, there are cases where even building one of them could make sense if the value of that one could justify its development cost. And there are actually, places in the government where they built special purpose accelerators of that variety. But for most commercial applications, you need enough people who want that they can kind of share the development cost by buying a lot of them. Yeah, Ronnie.
So what kind of special purpose, I will explain what you asked, so what other special purpose accelerator do you have in mind, or those that justify? So we know that certainly the graphics you did, the deep learning and the genetics, what else?
Yeah, so the one in the solving and simulation, so I've done the ones I've thought of so far. I'd be really interested if you have any thoughts about what would be next. I'm constantly looking for a problem that's next. I know a lot of people have tried to tackle database acceleration, but that winds up being very much limited by memory bandwidth and storage bandwidth. I think that there may still be opportunities there. There are people who've looked at graph processing. But again, that tends to, again, be a memory-dominated application, so you're not going to get huge speed-ups, but there can be advantages of basically making the memory system a lot faster.
What about cryptographic accelerators?
Which? Crypto, yeah, well, people already build crypto accelerators, yeah. Yeah.
And what do you use like the programming ecosystem for these?
Yeah, so I would like to see a very, very high-level programming system.
I mean, who programs it?
Yeah, where you basically write something that looks a lot like Python, right? And then you can map it either into software that runs on the programmable parts, or into something which would be a high-level synthesis turns into a specialized unit. But I don't expect tools to automatically decide how to slice that. I think you need is what I call the mapping directives. You need to tell it, what if we made that function in hardware, and then it would synthesize that for you, and you can see what would happen. You can do a lot of what-if studies.
You have
We don't have the whole thing built yet, but we're starting to experiment with that. We have a project within NVIDIA Research on high-level synthesis, and we're getting very good results synthesizing from C++ and System C to hardwired units for different things. Yeah.
So regarding sparsity support for matrix and machine learning workloads, you gave us sort of two conflicting views. One is that you described the EIE, which is fully featured sparsity blanket, and then on GPU, basically first you convinced that the GPU is a very good solution, but then GPU really does not take sparsity into account.
Yeah, I have to be careful what I talk about because I can only talk about announced products. But sparsity is important, and you know what you always see in our GPUs is a few generations behind where we actually are. Yeah.
You talked about adjusting the algorithms to that. There seems to be a chicken and egg cycle. One approach is you come up with a computational solution structure, and then people try to adapt their algorithms, like MapReduce, let's say. Try to make everything match.
Right. When you have a hammer, you make everything look like a nail.
Yeah, and the other is you have needs and try to design hardware to match them. Which do you think?
Yeah, no, I think that there's a tension there, right? So even if I have an environment where it's very easy for me to describe new accelerator blocks and synthesize them, have them fabricated, and maybe stick them on top of an existing, GPU substrate. Once I have a block, a lot of people are going to spend a lot of effort figuring out how to fit their application into that block, and that will then change the way the applications are. One thing we saw when we first opened up people to program GPUs with CUDA is people would reprogram their applications in CUDA, and by doing the restructuring they needed to do that, which is really thinking about how to expose the parallelism in their application, it actually ran way better on a CPU as well. They'd actually gotten a lot of chaff out of their applications just by rethinking it in parallel. And so we hope that by trying to restructure it around the existing blocks, people will actually improve their understanding of their applications. And then only when there's a real need for a new block will they come up with it. But there is a bias. People will be biased to make stuff run on the existing blocks. Yeah.
So to what extent do you expect the change to data center kind of based computing rather than personal computing would change the way you would build those accelerators to be shareable and to support operating system principles and abstractions and sharing? To what extent those things would also require acceleration and hardware as well?
Yeah, so the question is, how do you basically make these accelerators work in a data center environment? So I'll point out that many accelerators will work in an embedded environment as well. The ones in the data center, if they have to be shared by multiple processes and multiple protection domains, I think it really, we do this today, and it's done by having the accelerators be the form of blocks which act like instructions, right? So if the instruction is executed by a process, it means that you have permission on all the input operands that you're feeding it out of registers and where you're going to put the output results. And so just by adding it on as an instruction, you inherit all the mechanisms around protection and sharing and virtualization that's already there. And so you'd like to attach things in a way that you can inherit the existing mechanisms.
Okay. Thank you.
Okay, well, thank you.